Welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I'm your host, Mr. Takeda, and I'm going to teach you some algebra right now. This is lesson 3.2 on linear functions, in which we ask the essential question, how can you determine whether a function is linear or nonlinear? Well, first, I think we have to talk about some vocabulary. So let's start there. We've got definitions here and three vocabulary, terms would be better, better way to say it. First is a linear equation in two variables. And for the purpose of this, the variables are x and y. It's an equation that can be written in the form y equals m times x plus b. So in this case, the m and the b represent numbers of some sort, while the x and the y just stay those variables. So, also important here is that the x, there's no exponent here. It's just x to the first power, really, right? We don't really see an exponent, and y to the first power. We don't use those, but that's what those are. Second, a linear function. It has a graph that is a non-vertical, and I'm going to stick in here a non-vertical straight line, just so we are making sure that we're all talking the same thing here, that when we say line, it has to be straight. And this is due to a constant rate of change. So we'll talk about this some more in a bit. But that constant rate of change is what causes the line to be straight. And then finally, we have nonlinear function. Well, if a linear function has a straight line, well, a nonlinear function will have something else. It's anything other than a straight line, because it does not have a constant rate of change. All right, so if you need to pause the video here to finish getting these into your notes, please do so, and then join me on the next page. Hey, there you are. We're going to go through example 1 here from the book, in which we were asked the question, does the graph represent a linear or non-linear function? Well, for example A, we've got this curve here. And you'll learn in the future that this curve is called a parabola. Look at that. Bonus content for you guys. A parabola. It's this curve. And that is not a straight line. So this is nonlinear. Look how easy this first example is. These first examples, they lull you in with a false sense of security. And then they get to those last ones and they mess you up. What about B? Well, that's a straight line. So this is linear. And for the purposes of explaining on a graph, nonlinear, that's not a straight line. Linear, it's a straight non-vertical line. Okay, if you need to finish this up in your notes, please pause the video, rewind it, whatever. And then when you're done, join me on the next page. Oh, example 2. This is a good one. Identifying linear functions using tables. We have two tables here, and we're asked, does a table represent a linear or non-linear function? And then explain. Okay, so let's get back to this idea of a constant rate of change. And I'll explain what this means here right now. So we want to look at, we have a series of x values. We can think of those as our input. And the series of y values, those are the output in these functions here. Okay, so what's happening with the x is I'm increasing by 3. I'm increasing by 3. And I'm increasing by 3. So as my x value increases by 3, what's happening to my y value? Well, from 36 to 30, it's a minus 6. From 30 to 24, also a minus 6. And from 24 to 18, also a minus 6. When we write these as a ratio, we put the output over the input. We say that there's a negative 6 change in the output for every positive 3 change in the input. So we can simplify this down to negative 2. That's a constant rate of change. It's all of these are the same. Negative 6 over 3, negative 6 over 3, negative 6 over 3. It's a constant rate of change, so this is indeed linear. Let's look at B. Okay, so my input, it's increasing by 2, it looks like. 1 plus 2 is 3. 3 plus 2 is 5. And 5 plus 2 is 7. Okay, so far so good. But look, you got to look. 2 plus 7 is 9. 9 plus 11 is 20. And 20 plus 15 is 35. So this is 7 over 2, 11 over 2, and 15 over 2. Not a constant rate of change. Now, when I say constant, constant means all the same. Constant means it's always the same. Okay, so this is not constant. These are changing, right? So this is non-linear. Does not have a constant rate of change. Okay. Now let me just give you a little hint here, a clue here. When you do these, you got to check them all, okay? Because maybe the first two will be constant, but the third one won't be. And that's where sometimes kids get a little sloppy, a little lazy, and they'll check the first two and they go, oh, this is constant, this is good. But they don't check the third one. You got to check them all right? Little hint, little clue. Hey, let's take a look at example 3. Identifying linear functions using equations. Now, the first definition of linear functions regarding equations is that it can be written as y equals m times x plus b, where m and b are numbers, right? They're numbers of some sort. Right? They're numbers. And there's no exponent here on the x or the y. Very important. Okay, so the first one is tricky. Y equals 3.8. Is there an x there? There's not. But I can think of this as y equals 0 times x plus 3.8. Right? So there's a number and a number. Y to the first power, x to the first power. So this is indeed linear. Very tricky. Y equals the square root of x. Now, if I was trying to like solve for y, it's already solved for y, and this is not x. It's the square root of x. Or later on when we study exponents, you're going to learn that this is actually x to the power of 1/2. So it's not x to the first power. It's x to the power of 1/2. So this is nonlinear. What about number 3? Y equals 3 to the power of x. This is what we call an exponential function because the input variable is in the it's an exponent. It's not the main number here. So this one is again nonlinear. And again, you should write down the reasons. I'm not writing them down for sake of time, but you should write them down. If you need to pause, you can do that. And for number 3 here, it's because the x is the exponent. It's not a variable itself. It's the exponent. That's not to say it's not it is a variable, of course, but it's not something we're multiplying. It's something that is an exponent. Okay, y equals 2 divided by x. Well, if you think about this, this is really y equals 2 times what? 1 over x. So this isn't the, another way you can think of this is y equals 2 times x to the power of 1/2, right? It's in the, it drops it in, I'm sorry, this is not 1/2, that's this one. This is, sorry, let me fix this, sorry. X to the power of -1. Yeah, so again, it's shown as the reciprocal of x, or I can write it as x to the power of -1. But in either case, this is nonlinear because it's not x to the first power. What about 5? Well, it's got this distributive property thing happening here, so let's distribute it. Y equals 6 times x, 6x, minus 6 times 1, minus 6. Yeah, look, see, y equals, that's y, equals m times x plus b. Yes, plus -6, right? So this is linear. And what about the last one? Okay, so the last one, again, I said, if you have x squared, that's kind of your clue here. That's kind of your clue here. But let's solve for y. If I add y to both sides, x squared equals y, well, this is nonlinear because it's not x to the first power. So this is nonlinear. This is something we call the quadratic, and this will generate those parabolas we looked at the previous screen. Okay, let's take a look at this. You need to pause this here. You need to look at these, determine which ones are linear functions or not. You get those letters written down. This will be your exit question at the end of the pod. Pause it if you need to. Example 4, graphing discrete data. This is from page 114. The linear function 15.95x represents the cost, y in dollars, of x tickets for a museum. Each customer can buy a maximum of 4 tickets. Find the domain of the function. Is the domain discrete or continuous? Well, if x is the number of tickets and each customer can buy a maximum of 4, then let's do it this way. Domain is going to be x equals 0, 1, 2, 3, or 4. The customer can only buy 1, 2, 3, or 4. That's the domain. And this is what we call discrete because these are separate numbers. You can't buy like 1 1/10 tickets or 2 5/9 of a ticket. You can't buy fractional parts. You can only buy them in whole numbers. So this is discrete. And it says graph the function using its domain. We'll do that one in class. Okay? But I want you to know what discrete functions are here. And that means the next one is going to be continuous data. Continuous data. A cereal bar contains 130 calories. The number of calories consumed is a function of the number of bars eaten. Does this situation represent a linear function? The answer here is yes. Because I can write this as y, I'm sorry, not y, c, the number of calories is equal to 130 calories per bar times the number of bars. That's y equals mx plus b. Now, this b here is a different b. This b is bars eaten. But this is like saying y equals 130x. And then plus 0, which would be my number. There. Okay, so is this domain discrete or find the domain of the function? Is this domain discrete or continuous? And this one is continuous because you can actually eat parts of a bar. You don't have to just eat whole bars at a time. And so for this one, the domain is going to be x is greater than or equal to 0, right? So we express this as an inequality because we want any number greater than 0, whether it's a whole number or not. And we'll talk about the graphing of this in class. Okay, well, that's it for now. I just wanted to get the discrete and continuous part in here, and we'll do the rest in class. Thanks a lot, and have a great rest of your day.